Hi, I'd like to take a few minutes to talk about a geometrical interpretation of the definite integral. We write the definite integral as the integral from a to b of f of x dx, and we can interpret it geometrically as a positive minus a negative, where a positive is the positive area and a negative is the negative area. The positive area is the area above the x-axis here. So if we have our function f that's drawn right here, then it's the region A1 and A3. So we can write those right there. And the A neg would be the A2 and the A4. Okay, so using this idea, we can interpret the definite integral geometrically. Let's look at a couple of examples where we can apply this directly. The first is our recent example of the definite integral of this line, 6 minus 2x. And we calculated that the other day to be 21 using a Riemann sum approach. And remember, that was quite a long calculation. Let's look at it another way. Let's think about drawing this line on a graph. And we'll put f right here, and we'll put x here. And we see there's a y-intercept of 6. And let's work out the value of the function at the endpoint. And so this is our function f here. And so f of 5 is equal to 6 minus 2 times 5, which is going to be minus 4. And f of minus 2 is going to be 6 minus 2 times minus 2, which will be equal to 10. And so this value up here is 10. And we have a point here at minus 2, 10. And we also have a point here. This is 5. And we have a point minus 4 on the y-axis. And so we have a straight line here that looks like that. So we can think about this as two triangles. And notice that the y-intercept here, the value of x, which gives f equals 0, is 3. So I'll put that in as well. Our first triangle is the one shown right here. And this is going to be our A1. And then our second triangle is the one shown here. And this will be our A2. And so the integral is equal to A1 minus A2. Now we need to calculate these areas. And so we have a triangle here with a base that has length 5 because it goes from minus 2 to 3. And so we have the base is 5, and then the height is 10. And then we divide by 2 to get the area. So A1 is going to be equal to 25. How about A2? The base goes from 3 to 5, and then the height is 4. And so A2 is going to be equal to 2 times 4 over 2, and that'll be 4. And that's going to give us 21. And so we've used a geometrical approach instead of a Riemann sum approach, and we've got the same answer, which is very cool. So let's look at the second integral here, the integral from 0 to 1, the square root of 1 minus x squared dx. We want to interpret this geometrically. So if we call this y, then we can say y is equal to the square root of 1 minus x squared. If we square both sides, we have y squared is equal to 1 minus x squared, or x squared plus y squared is equal to 1. That's the equation for a circle of radius 1, centered at the origin. So it looks something like this here. There's 1, there's minus 1, and 1. And if we're interested in the arc y is equal to the square root of 1 minus x squared, it's this one right here on the top, because we're taking a positive square root. So this is equal to, y is equal to the square root of 1 minus x squared. On the bottom here, we have y is equal to minus the square root of 1 minus x squared. And we're not interested in that. We're just interested in the plus sign. So I'm going to draw that out again here. And the question asks us to take the definite integral between 0 and 1. And so the area that we're interested in is exactly this area here, shown there. And so we know the area of a circle is going to be pi r squared. And so the area of a quarter of a circle will be equal to pi times 1 squared over 4, which is equal to pi over 4. And that's our answer. And we derive this just using the geometrical interpretation of the definite integral. And sometimes for problems like this is the easiest way to compute a definite integral.